So thank you all for joining this week's Applied PD seminar at the University of Washington. I'm delighted to introduce a speaker today, Ibrahim from the University of Victoria. He did his PhD at the University of Tunis. He works in a variety of very interesting problems in partial differential equations. I thought he was going to be speaking to us from Victoria today, but apparently he's he's speaking to us from Abu Dhabi, where it is currently 10 p.m. So thank you, Slim, and go ahead.
Thank you, Bernard. Thank you all for coming, and it's really a pleasure. And hopefully next time we'll be face to face and give another talk maybe. So today I will talk about a few works that I have been involved with, like the past 10 years. So it's about singularity formation for the primitive equation. And so the old result, I'll try to explain why we were not happy, and we needed to revisit this the old result, and I will share with you new result about singularity formation. So the plan today is to go to walk you through the primitive equation. If you don't know them, then I will walk you through that. And then I will recall what do we know about these equations, and from local well-posedness, global well-posedness, viscous, inviscid, and so on and so forth. All the results that we know so far. And then I will focus on the singularity formation and try to give you a few updates about that. Okay. So the two works that I'm going to share are with Cao, who's in Florida, Charles Golo, who is in Paris, Chuan Lin, who is in Santa Barbara, and Kenji Nakanishi in RIMS, Kyoto, and Idris Titi in Cambridge. So the most recent one is with Charles Golo and Chuan Lin, and these are the pictures. I couldn't, sorry, I couldn't find the photos for Kenji Nakanishi and Cao. I just found videos for them giving lectures. Good. So this is the plan. So I would, as I said, I will walk you through the derivation of the primitive equations as a physicist, and then I will mainly focus on the viscous case. Then I will recall the known results about well-posedness, ill-posedness, local well-posedness, and finally the finite time singularity. And I will recall two results here in this part, and will briefly explain the ideas of the proofs. And then, as I said, so I will talk about self-similarity singularities for the primitive equations. Good. So the starting point is Boussinesq equations. So Boussinesq equations are accepted model in geophysical flows or atmospheric and oceanic dynamics. It's also used in central heating industry and cupboard ventilation. So this is the primitive equation consists of equation of conservation of momentum, right? So the conservation of momentum tells us that this is nothing but Newton's law. So we have the acceleration here. So U is the velocity of vector field. So this is the acceleration, and mass times acceleration by Newton's law is equal to all forces. So we have the viscosity here, we have the advection, and then we have the pressure, which is multiplied by the density. Rho is the density, and here we have Coriolis force. So omega is the strength of the Coriolis force, K is the vertical vector, and T is the temperature, G is the gravitational constant. And this fluid is set in a D dimension, okay? So it's set on a domain D, special domain D, and this is time, right? And the special domain, it can be the torus, the d-dimensional torus, or the whole space, infinite channel, and etc. You can imagine it's a cylinder and so on and so forth. Okay, so this is the momentum equation, and then we are working with incompressible fluids. So the fluid enjoys this divergence-free condition. And this momentum equation is coupled with the temperature, as you see here. And the temperature is affected or transported by the velocity vector field. And it's diffused with the constant kappa here. Okay? So Q here is an external heating. And as I said, rho zero is the density, and in the Boussinesq approximation, the density is assumed to be constant whenever it's coupled with whenever it's in front of the pressure. Okay, so this is the Boussinesq equation, and as I mentioned at the beginning, so this model is accepted both in geophysical flows and in industrial models. And now, depending on the problem that you are studying, for instance, if you are doing an experiment in a lab or studying the fluid in the ocean, so maybe you can further simplify these equations. And this is exactly what has been done for large-scale oceanic circulations or for geophysical flows. There is a distinction between the horizontal scale and the vertical scale. Okay, so when we talk about atmospheric models, then the height is about 10 kilometers. However, the horizontal scale, it's about it's about thousands of kilometers. So there is a difference between the horizontal and the vertical scales. And using this, one can simplify the primitive equations further. Okay. So let me try to explain to you how this reduction using this different scales between horizontal and vertical motions. So here in this slide, so I'm just rewriting the previous set of equations, the momentum equations, by just distinguishing between the horizontal motion. So this is the horizontal motion, and this is the vertical motion. Okay, so UH is the horizontal velocity, the horizontal component of the velocity, and W is the vertical component of the velocity. Okay, so this is nothing but the previous slide, but just distinguishing the two motions. Okay. So now let's do like a typical scale analysis. So in the case of the oceans, so the typical scales for typical horizontal distance is about hundreds of kilometers, thousands of kilometers, sorry. And the horizontal velocity is about 10 - 1 meters per second. The depth is about a few kilometers, right? Coriolis parameter has this, it's about 10 to the -4 per second. The gravitational force is about 10 meters per second square, and the density is about 10 to the power 3 kilograms per meter cubed. Okay, so now using these typical scales, let's calculate the typical values. Okay, so for the typical vertical velocity, so the velocity is u times the height divided by L. So when you calculate that, you get 10 to the power -4 meters per second. Do the same thing for the pressure, and you get 10 to the power 7 Pascal. And then the time scale is about a few weeks, I think 10 to the power 7 seconds. Okay, so these are typical values. Now let's plug in these typical values in the horizontal motion and the vertical motion. And let's start first with the vertical motion. So So this is the momentum equation. It's a vertical component. So let's substitute typical values here. Okay. So the first term is the vertical acceleration, and its typical value, it's about 10 to the power negative 11. The advection term here, it's about 10 to the negative 11. Similarly for the advection, still the advection term here. And now when we look to the last two terms, so the typical values are about 10, okay? And if you want this to be zero, then it makes sense that the first three terms in this equation, right, are of order magnitude of 10 to the power negative 12 compared to this one. This is the ratio between the two. Okay, so it makes sense to neglect this vertical acceleration. Okay, and when you do so, you get what is called the hydrostatic balance. Okay, so this is the hydrostatic balance, which says that the variation of the vertical variation of the pressure is balanced by the temperature, basically. Okay, so this is a typical scaling analysis, and let's do the same thing for the horizontal motion. Okay, so when we do for the scaling analysis for the horizontal motion, we get terms like this. So the first three terms, horizontal acceleration, horizontal component of the acceleration, diffusion, and advection, they are of order 10 to the power negative 8, while the last two terms, the pressure and Coriolis force, are about 10 negative 2 and 10 negative 5. So the ratio between these two, it's not of order 10 to the power 12 as we have seen for the vertical motion. So it's reasonable to keep all the terms as they are almost balanced. Okay. So now using this scaling analysis, then one can further simplify Boussinesq equations into this new set of equations. This is the set 1. So this is the set of the primitive equation. So here I have used the hydrostatic balance, meaning that I've neglected in the vertical motion, I've neglected the vertical acceleration, basically. Okay, so this is called the primitive equations, and here I have just normalized all the constants, the viscosity and so on and so forth, and the gravitational constant here. Okay, so this system was derived. So this is like a physicist derivation, but it was derived rigorously by Azirar and Guyan for weak solutions, and quite recently by Lee and Titi for strong solutions. And Lee and Titi, they provide an error estimate with respect to the aspect ratio. The aspect ratio is the depth compared to the width. Okay, good. So this is now our object of study, and let me recall what do we know about these primitive equations. So the first works, they go back to the late 80s, 90s by Pierre Williams and Timam Wang, who constructed the weak solutions for the three-dimensional model. Okay. Then Didier Bresch and Guyen Gonzalez, they showed the uniqueness of weak solution. Okay. The question of the uniqueness of weak solutions for the 3D, it remains unresolved, like for Navier-Stokes, for instance. Okay, now in terms of strong solutions, so Guyan Gonzalez Masmoudi and Rodriguez Bellido, they showed, they constructed local solutions for the viscous primitive equation. And Didier Bresch, he showed global existence of weak solutions. Okay. The most striking work in the case when you have viscosity is by Cao and Titi in early 2007-8, I think, where they showed that whenever you have viscosity, then the primitive equation, they do not develop any singularity. In other words, you do have global regularity whenever you have a viscosity. So Cao's and Titi's result was later generalized to extended to other domains by Kobelkov and Kukavica, Zian, and more recently by Heber and Kawishaba using different techniques. Okay. This is the case of full viscosity. Now there are other results when you have partial viscosities. Okay. So there are a bunch of results over there, and probably I will skip the details. And this has been led by Titi and Cao and Titi Li and Cao. Okay. So this is the state of art whenever we have viscosity. Okay. And then the question, what happens if we don't have viscosity? Okay. Good. So that leads me to focus more on what we want to study. Okay, so here our specific setting is the inviscid non-rotating primitive equation. Okay, so as you can see here, I have neglected or dropped the viscosity. Okay, and then also the temperature really doesn't harm. Okay, because the temperature is just transported or vectored by the velocity vector field and diffused if you have a diffusivity, right? So in terms of analysis, it doesn't really harm, and we will assume it constant, and we can take this constant to be 0. Okay, so when we do so, then the primitive equations, they can be simplified to system number 2. Okay, so here I dropped the viscosity because whenever we have viscosity, there are no singularities, right? And then I took a constant temperature. Okay, so this is the momentum equation. This is the hydrostatic balance. And the third equation is the incompressibility, where I distinguish it between the horizontal and the vertical component of the velocity vector field. Okay. Okay. Now I'm going to fix my domain. So my domain D, the spatial domain, I write it as M cross 0, 1. So 0, 1, this is for the vertical direction. So whenever you study the ocean or you study the atmosphere, so you can think that your domain is bounded between 0 and H, but you can, in terms of analysis, you can take H to be 1. Okay, and M can be the whole space R2. It can be the so in that case we will have infinite channel, or it can be a cylinder, or it can be the torus, and so on and so forth. So if I choose my M to be a domain that has a boundary, then this is the kind of boundary condition that I'm going to choose. Okay, so on the top and at the bottom, the vertical velocity is 0. Okay, and at the lateral boundary of the domain, then we choose the average in Z of the horizontal velocity is its normal component is 0. Okay. So these are now the inviscid primitive equations, right? And some other communities, they call them the hydrostatic Euler's equations. Particularly the French community, it's more known than that with the hydrostatic Euler equations rather than the primitive equations. Okay. Any questions so far? Okay. Good. So So now I want to recall the known results about the Inviscid primitive equation. Okay, so the Inviscid primitive equation. So let me go back here. So there is a loss of derivative here for this equation, and this loss of derivative, it made the analysis challenging to solve these equations in the usual Sobolev space. Okay, so the local well-posedness of this primitive equation in the scale of Sobolev spaces has been a challenging problem, and that has been open for years. And the main problem is because we have a loss of derivative here that we cannot recast whenever we work in Sobolev spaces. So people then try to show that the problem is ill-posed. Okay. And probably the first result in this direction is due to Rinaldi, who showed the instability, the ill-posedness for the primitive equation. And the way he did that, he considered a shear flow. Okay, so you take a shear flow, so UWP to be capital U. So this capital U is a function that depends on Z. That's a shear flow, and WP are both 0. Okay. So he took this specific shear flow and he perturbed it around it. Okay, so the tilde is a perturbation here. This tilde is a perturbation around this shear flow U. Okay, and he considered the perturbation system, which is equation number 4. Okay, and he was able to construct an unstable eigenmode. Okay, so he's an unstable eigenmode, and this eigenmode it grows like K. Okay, K is the Fourier mode. Okay, and so this type of instability, it's Kelvin-Helmholtz type instability, and that type of instability, it gives us an idea what would be the best or a good space or a good candidate for space to solve the primitive equations. For instance, to kill this kind of instabilities, so one has to take initial data that are exponentially, right, decaying in Fourier mode, and this type of decay in Fourier mode corresponds exactly to the Gevrey class of order S with S bigger than 1. Okay, so this is a good indication that if you want to solve the primitive equations, the Inviscid primitive equations, given these instabilities, then you would consider a Gevrey class space with index S bigger than 1. Okay, good. And the case when S is equal to 1, this corresponds to a space of analytic functions. Okay. Now, if we compare this primitive equation to a sister equation, which is a Prandtl equation, then this program or this heuristic has been made very rigorous in the sense that for Prandtl equation, you have instabilities that grow like square root of k. So these are less serious or less harmful instabilities than the primitive equation. So this suggested that if you want to solve these Prandtl equations, then you would solve them in the Gevrey class of order 2, okay, without imposing any condition on the initial data. Then you would work in the Gevrey class of order 2, and this has been made, as I said, rigorous. So Dieter and Gerard Varé and Dormy, they were able to solve the Prandtl equation in Gevrey class of order 2, and they basically they showed that this is the best space where you can solve the Prandtl equation. Okay. Now, for the primitive equation, as I said, this kind of instability, it suggested that if you want to solve them, then we need to work in with analytic functions. Okay, and this is exactly what has been done by Kukavica, Vikol, and Wang. Yeah, Vikol, Wang, and Kukabika, Timam, Vikol, and Wang. Okay, so they were able to show that the Inviscid primitive equations with analytic initial data is and the boundary condition that I specified are locally well posed, and they were able to construct a solution. Okay. In terms of nonlinear instability, Han Kwan and Yuan, they upgraded the linear instability to a nonlinear instability. Good. So there is another type of well-posedness. It's this type of well-posedness if you impose some monotonicity conditions on the initial data. Okay, and this program has been done successfully by Masmoudi and Wang, and I think Brunier also, Grenier, they were successful by imposing some monotonicity condition on the initial data. Then you can solve the primitive equations even in Sobolev space. Okay, so these are the two types of well-posedness that are provided. But if you don't assume any monotonicity, then initial data has to be in the analytic space. Good. So we have seen that these Inviscid primitive, so if we summarize, we have seen that the viscous primitive equations, they do not develop singularities, right? And they exist for all time. They're nice. In the Inviscid case, there are strong instabilities. And if you want to solve your problem, then you need to work with the analytic initial data, okay? Other than that, you probably need to work with data that has that satisfies some monotonicity conditions. Good. Now, in terms of singularity formations, so about 10 years ago, we were thinking about this, and together with Tsao and Nakanishi and Titi, and 2 weeks after we posted our paper on arXiv, Wang, he posted his paper also, and he showed that the primitive equation should develop singularity in finite time, okay, using a slightly different approach than ours. And I hope I will have the chance to explain this very briefly. So in terms now of singularity formation for fluid equations, so this has caught the attention of many eminent colleagues, and there are great recent results in this direction. So I would mention the result by El-Gendi, Taraq, who showed existence of non-smooth blow-up for 3D Euler equations, okay? And El-Gendi, Goul, and Masmoudi, they showed the stability of this non-smooth blow-up for 3D Euler equation. Now, Kolo, Goul, Masmoudi, they also studied the Inviscid Prandtl equation and Burger's equation, and they constructed many stable and unstable profiles that blow up in finite time. And together with Kolo and Goul and Masmoudi, so we constructed stable blow up for the viscous Prandtl equation. Now, there are other types of results about compressible Euler equations. So by Buckmaster, Scholar, and Vlad Vikol, they have shown that there are shocks for compressible Euler equations. Okay.
Slim, can I ask you a question?
Sure, yeah.
What do you mean by non-smooth blow-up?
Very good question. I'll come to that. Very good question. Thank you. Thank you for asking. I'll come to that. Good. So these are now the old results about 10 years ago. So the first one is my result with Tsao, Nakanishi, and Titi. And it says like if there exists a smooth, so we can construct explicit initial data for which if you have a smooth solution, then this smooth solution has to develop singularity in finite time. And Wang's result, it reads as follows. So as you can see here, so let me take initial data such that the horizontal velocity at some x hat point is constant. So it does not depend on z at some fixed point. Okay, so this is this type of initial condition. And then you assume that this point x hat is somehow a stagnation point. And the most importantly is that the x derivative of u0 at this specific point x hat is concave down. Okay, so this is a kind of monotonicity condition that I told you if you want to solve the Inviscid primitive equations without with the monotonicity. So this is the type of assumptions that you would take. So he's saying, like, if we take this initial data, right, then there is a finite time for which the n-infinity norm of the solution has to go to infinity, or the pressure gradient has to go to infinity, or the x derivative of the solution will go to infinity along some characteristic. So capital X here is a characteristic. Okay, good. So let me briefly sketch the proofs of this result. The proof is the two proofs are actually not hard to read. So our proof goes in two steps. So the first step will instead of working with the full primitive equation, so we'll try to do some reduction using the symmetries of the equation. Okay, and these reductions will allow us to derive, like, going from 2D to 1D, for instance. And let's hope, like, for this 1D PDE, we can show formation of singularity quite easily than the full 2D problem. So this is the idea. So as I said, we can assume that the temperature is constant because it doesn't really harm in terms of regularity. And let's assume that the v component of the velocity is 0, okay? And the velocity is y independent, okay? So these assumptions are propagated by the equations. So if you assume these assumptions at t equal to 0, then you can show them that propagate at any time t. And finally, we will assume that the horizontal or tangential velocity is odd function, while the pressure is an even function. And the vertical velocity is an even function. And as I said, if you plug this into the equation, then you will see that they are invariant by the flow. Okay, and we'll keep our boundary condition. So the vertical velocity on top and at the bottom is 0. Good. So once we have these symmetries, then so the main difficulty. Okay, let me just put a remark here. The main difficulty, I mean, if you look to what happened to Prandtl equation, so the singularity formation for Prandtl equation has been known, like, for a long time, basically. Okay, and Prandtl equation, the pressure is given because for Prandtl you have an outer flow that is set at infinity, basically, and it's known. It's not an unknown. Okay. And for the primitive equation, the pressure is unknown, okay? And it's part of the system that you want to solve. And the techniques that have been applied to Prandtl, they just fail if you want to apply them for the primitive equations. So we need to somehow handle the pressure, okay? And using these symmetries, we were able to do that. So using the symmetries, we were able to solve the pressure in terms of the velocity vector field, okay, the horizontal velocity. So, so some computation tells us that the derivative of the pressure is given by -2, the z average of UUX, okay? So just a computation. And then once we have the pressure, we plug it in back into the PDE, into primitive equations. So we get this equation number 9, okay? So this term, think about it as the pressure term. And now using the symmetries, so we have said that u at x equal to 0, u is an odd function, right? So u at x equal to 0 is 0, so you can drop this this vector, right? And you can end up with the closed first order partial differential equation, which is the blue one. Okay, so here I have set capital W, the restriction of the vertical velocity at x equal to 0. Good. So using my symmetries, right? So we were able to reduce the the primitive equations into this blue system here with this boundary condition. Okay. And now we said, okay, so can we show like finite time singularity for this reduced model? Okay. And I want to you to remember that whenever you see this term here, think that this term is the pressure. It's coming from the pressure, as it's mentioned here. Okay, so this integral of wz square is nothing but the pressure term. So just keep an eye on that. Good. So then, okay, we said, so let's take this PDE. Let me just come back here. So if you have a solution W, then you replace W by lambda and you scale time by lambda, okay? Then you can see that this leaves this PDE invariant, okay? So you will have lambda square coming out from every term, right? Here, 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 here. So this scaling keeps the PDE invariant, and then, okay, this suggested to look for a self-similar solution in this form, okay? So let's look for W in this form. And this is the boundary condition, exactly this boundary condition, okay? So this gives us, when we put this ansatz into the PD, this gives us this differential equation 12 with m square is nothing but the pressure term, okay? And then, okay, we observe the following. So if you put the pressure term here, then the mean value is preserved, and this means that this value here of can be anything, okay? So we said, okay, so let's put this as a parameter, positive parameter, and try to find if there are solutions to this differential equation, okay? And so not hard to show that indeed there are, for any fixed m positive, then you can construct a solution that has this regularity. It's C2 alpha, and alpha depends on m, okay? So this is the alpha m. Good. And now, once we have non-trivial solution phi to this, then we immediately have a blow-up, finite time blow-up solution to this reduced model, right? And then you can lift this blow-up solution to the 2D model, as I will show you in a second. Good. Now, you may wonder that whether for this initial data, for the primitive equation, so we need to go back to the original system, right? Whether for this initial data, you will have a unique solution for the primitive equation. And this is the hard task. And this is the weak thing about this result. And that's why we needed to revisit it somehow. However, if you focus on this reduced model, then this reduced model is well posed in H2, okay? And for this initial data phi, you are sure that there is only one solution to this reduced model, okay? And the thing is that when you do this reduction and when you do the restriction on the axis x equal to 0, the loss of the derivative that we had in the primitive equation, it just disappeared, okay? Good. So this is this is the first result. So now let me try to explain Wang's approach, okay? Wang's proof to show finite time singularity. So remember that Wangs, he picked the very special initial data, right? So you have a point x hat. Let me draw a picture here. So suppose you have a river here, right? And you assume that there is a point x hat here, right? In which the velocity is u hat, and u hat does not depend on z. So the velocity at any point here, it's the same value u hat. Okay. So what he showed is and then he assumed that this concavity condition, like if you take dx of u at time 0, right, it should be concave down, and x hat should be a critical point of dxu. Okay. So his proof goes as follows. So he said, okay, let me change the coordinate system using a Lagrangian approach. Okay, so you follow the characteristics. So let me change it. So you take characteristic line here, issue of this point, and you follow the Lagrangian coordinates. So you can change the coordinates. Okay, you can change time, the position x and z, just by using Lagrangian approach. And then what this means is that instead of having an observer sitting here, right? So your observer will move with particles, fluid particles. Okay, and if so, then this observer will see the point x hat u and the velocity u hat to be set at 0. Okay. Okay. And this Lagrangian change of coordinates, it keeps the equation invariant. Okay. So it doesn't change the equation. Good. So this is what is called the freezing lemma. So this is the first step. And the second step, remember the conditions on the initial data. Using this freezing lemma, he was able to propagate these conditions, these two conditions exactly. He was able to propagate them from time 0 to any time t below the time of existence. Okay, nice. Now, if you propagate this concavity condition, then there is a very nice calculus identity, okay, that enables us to get rid of the pressure term. Remember that this is the pressure term, okay? So you can estimate the pressure term by an estimate on the velocity itself, okay? And then by doing so, you can get a Riccati type differential equation, and this Riccati type differential equation has a finite time blow-up. And then he concluded like that for the primitive equation, either this goes to infinity, or this goes to infinity, or there is a shock. Okay. Good. Now let me comment these two results. So first, as I said, in terms of our results, so we can lift it, we can upgrade it to the two-dimensional or even three-dimensional primitive equation. Okay, so if you take this initial data, okay, so this is the initial data, two-dimensional, right? This is our profile phi m, and you choose W0 to be this. So you will this will satisfy the divergence free and so on and so forth. And if you say, okay, if there is a smooth solution with this initial data, then the solution cannot exist for all time, right? Good. However, as I said, the bad thing here is that the well-posedness does not apply to this initial data. Okay, so for this initial data, you may have other solution. Indeed. Okay, but for the reduced model, we cannot have another solution. There is a unique solution. Okay, so that's why this is the thing that we didn't like about that. If we look to Wang's result, it's better in the sense that you can pick this initial data. Okay, this is an explicit initial data, and this initial data is analytic. Okay, there is no doubt about that. And then for analytic data, we are sure that there is only one solution. And Wang's result tells that this solution either has infinite velocity, right? Or the gradient of the pressure has is infinite, right? Or something else. And these are somehow non-physical, somehow non-physical things. But if we want to draw a conclusion, so the two results tells us that there is something happening for the primitive equation. Okay, there is something happening, and this led us to the recent work, and we wanted to understand what's going on. Another remark here before we go to the most recent result is, so you can rescale this initial data by a factor lambda, and you can measure how the time of existence varies with lambda. Okay, so if you increase lambda here, then the time of existence shrinks. Okay, so another remark here, this initial data, if you take the z average of the initial data, okay, if you take the z average of this, you get 0. Okay, same in here. And this is not arbitrary actually, and this is quite specific, and it's a very nice property of the primitive equation in the sense that you have the primitive equations. Okay, so let me write it here. So you have uv. Okay, you can decompose this uv into barotropic and baroclinic component. You can write it as bar plus just some decomposition. So what is this? The bar is just the average with respect to z. Okay, and the tilde is the fluctuation. So this is called baroclinic. This is barotropic. And this is called baroclinic. Okay. And what is interesting is that the primitive equation, you can, using the primitive equation, you can write two equations on the barotropic and baroclinic. So the two equations are the following. So the bar will satisfy Euler type equation, 2D. And the tilde, it's a Burger's type equation. Okay, so that's just roughly speaking. And using this idea, so if you want to look for singularity, you are not going to look for it in the 2D Euler type equation because 2D Euler is globally well posed. However, Burger's equations may develop shocks in finite time. So if we want to trace or track any singularity formation, then we should look at it in this baroclinic component. And that's exactly these initial data. And that's exactly this initial data. Because if you take the z average of this initial data or this one, you get it 0. Okay, good. So let me now go to the recent result. So as I said, so the thing, we use the symmetries, we reduced the equation, we took the restriction of the velocity on the axis, or x equal to 0, right? And if you want to lift your initial data to the 2D or a 3D, then it's hard when you take a restriction, okay? So here I'm giving a remark that you can obtain exactly the same PDE without any restriction on the axis. For instance, if you look for solutions of this form, okay? So if you look for the tangential velocity to be like x times some function of z, somehow like separating variables, then amazingly, we can solve for the pressure in a quite similar way as restricting on the axis, okay? So you can solve for the pressure, and then you can show that this A here satisfies exactly the same PDE as the one that we got with Nakanishi, Tsao, and TT, or the PDE that Wangs obtained. Actually, we obtained all the same PDE, the result. Okay, so this is another way to get the same PDE without any restriction on the axis. So, and this approach is good if you want to extend it to 2D or 3D settings. Good. So now, as I said, so we want to revisit the two results about singularity formation for this PDE. Any questions so far? No? Okay. So let me explain the heuristic. As I told you before, the main challenge in studying the singularity formation for this equation is this pressure term. Okay, it's a non-local. Okay, so we have two non-local terms. This is non-local term, and this is non-local as well, non-local and non-linear, right? And and the most dangerous one is the pressure term. Okay, so what we said is the following. Okay, so we said, okay, is there any regime where we can neglect this pressure term? Okay, let's assume that there is a regime where we can neglect this term at the blow-up time. So let's assume that we know that there is a blow-up, and let's assume that there is a blow-up in which this is can be treated as a perturbation or lower order term. Okay, then at the blow-up, around the blow-up, so we can rescale the space to be 0 infinity instead of confined at 0, 1, because we are very close to the blow-up. Okay, and the equation will be simplified in this way. Okay, when you drop this one. Okay, now let's look to this PDE. So this PDE enjoys, it's more rich than the previous one in the sense that it has two parameter family of scaling. Okay, so if you have a solution A, then you can rescale A in this way. So you scale by 1 over lambda, the same scale for the space, and for time you choose mu. Okay, and now the scaling, it suggests for us to look for self-similar solution in this way. Okay, so this is basically my lambda, and this is my mu. Okay, so instead of mu, I'm working now with the parameter beta. Okay, so let's put this ansatz into, let's plug it into the PDE. Okay, and see what do we get. Okay, so now let me rescale the z variable by self-similar variable x equal to z divided by t minus t over beta to the power beta. Okay, so when we do that, so we get an equation on the profile. Okay, so phi, this phi is called the profile. This is the speed of the blow up, and this is the self-similar scaling. Okay, so when we put this ansatz into the PDE, we get the equation on the profile 19. Okay, and now Suppose we have a solution to this profile equation. Okay, so let's see when our heuristic would be valid and when it's not. So let's compare a square. Okay, so a square will be like, if you choose this with this choice, a square will be t minus t to the power -2. However, the pressure term, which is the integral of a square, it will scale like t minus t to the power -2 plus beta. Okay, and now the conclusion of this heuristic is that this ansatz here would be a good ansatz whenever beta is 0, whenever beta is positive, because this term will be negligible compared to this one. But when beta is 0, then the two terms, they scale in the same way. All terms actually, they scale the same way. Okay, good. So back to Bernard's question, this we will call it the smooth case. This we will call it the non-smooth case for a reason that will be clarified by this proposition. If you take the profile equation, then for any beta positive, you can construct a profile that is that has Holder continuous regularity. Okay, it has some specific behavior at x equal to 0. Sorry, this is x, and it has a specific behavior at x equal to infinity. So we can calculate that. Okay, good. However, when beta equal to 0, the solution is explicit. It's exponential minus z. Okay, so this solution is exponential minus z. And exponential minus z, this is a smooth profile, right? This is a smooth profile. However, here, the profiles are non-smooth. So for Euler's equation, when I said El-Gendi and Gould and Masmoudi, they showed the existence of non-smooth blow-up. Non-smooth blow-up means that the profile that they construct is non-smooth. It has regularity C alpha. Okay, good. And this distinction is really important. Okay, because when you look for a blow-up regime, stabilizing non-smooth profile is somehow easier than stabilizing smooth profile. Good. So let me state the theorem. So the theorem says as follows. So if we consider beta less than 1, this is just technical. I think we can extend it to any beta positive, but let me just stick with the simplest case. Then we can tune our initial conditions. So we can tune them to be very close to a blow-up regime, right? So I'm scaling the profile phi with lambda 0 and lambda 0. It's very, very small. The new 0 is like lambda 0 to the some power beta. And the initial perturbation is sufficiently small in C1. Okay. Then choosing initial data like this, then we are sure that the solution will blow up in finite time at some t infinity time. Okay, with the profile phi, with this speed, and with this scale. So this is the scale. Okay, t minus t to the power beta, up to a remainder term. Okay, that is much smaller than this profile. Okay, so it shows us, it gives us a lot of information about the speed of blow up, the profile of the blow up, and the scale of the blow up, as well as the control of the error. So this is a stability blow up, and this is the case, non-smooth case. Okay, good. Now you may wonder why we didn't try to stabilize the profiles CM that we have constructed with the Tsao, TT, and Nakanishi. We tried so hard, and we couldn't stabilize these profiles PM. And I think the reason is that the profile that we get, the blow up that we get is somehow non-physical because this function blows up at any z, right? So at any point, okay? So in some sense, this is a non-physical blow up. Good. And the second remark is that the smooth case, beta equal to 0, when we have this exponential minus z profile, seems to be the generic attractor for smooth dynamic. Okay. How much time do I have? Sorry.
So we are already about 10 minutes over.
Oh, I'm sorry. Can I get like 2 more minutes?
You said 2 more minutes?
Yeah.
Let's do 2 more minutes. Of course, the risk is that we are losing audience. Okay.
Okay. So let me very briefly explain the idea. So the idea is so we rescale our solution. So this is our solution. We rescale it with the self-similar coordinates. Okay. So we rescale time, self-similar time, and self-similar special variable. Okay. And then you decompose your B as the profile plus an error, and then you write the equation on the error. Okay. So this is the equation of on the error epsilon. So I split it into the linear part, potential term, still a linear part. It's a non-local, right? And 2 nonlinear terms. So these is the nonlinearity. Okay. And the same, we take the x derivative on epsilon. Okay. So this is the second equation. And we say the following. So the profile phi, it's a function that has a maximum at 0, and it does like this. Okay. So the blow up will happen really at z equal to 0 here. Okay. So the maximum of the function, we don't want to touch it, and basically. So that's why we impose for the perturbation to be 0 at where the maximum, where the profile has its maximum. So we do this choice, and this choice will fix us the 2 parameters, the 2 scales lambda and nu. Okay. So by fixing these boundary conditions, we get what we call the modulation equations, 2 modulation equations, one on lambda and one on nu. Okay. And then the analysis goes into 2 parts. So we split the analysis into an interior region close to the singularity, and an exterior region away from the singularity. Okay. And we measure the error differently based on the region. So on the interior region, we measure the error by some weighted Sobolev norm, right? However, in the exterior region, we measure the error by just the n infinity norm. Okay. So the idea is to construct, to control this error in the interior region. The idea is to construct a Lyapunov function. And here, the idea is to use the maximum principle that the equation enjoys. Okay. So the actual proof goes by bootstrap argument. So we prepared our initial data to be so close from a blow-up regime, okay? And we define initial closeness to this blow-up regime. So the initial closeness means this is the boundary condition, and this is the condition on the 2 scales, okay? And this is the condition on the initial size of the energy, okay, of the error. And then we define a trapped solution. Trapped solution means the scales, they will evolve in this order with, so lambda is roughly exponential minus s with some quantified constant capital K tilde, okay? And the same for the errors. Okay, and the big lemma is to reproduce to reproduce these trapped regime, but with better constants. Okay, so it's a bootstrap argument. So here we show that we can improve actually these constant capital tilde. Okay, so once we have that, so we do our energy estimate in the interior region. Okay, so this is basically an energy estimate where going from equality, this is an almost equality, except that we have dropped a term that has a good sign. Okay, and this term has a good sign by suitably choosing this point x hat. Okay, remember this equation is highly non-local, so everything is talking to everything. Okay, so now the idea is to construct the Lyapunov function. So we want to construct a spectral gap here. Okay, and to do that, we work on weighted Sobolev, as I said, and we specifically choose a very particular weight to generate a spectral gap. If you look to this huge quantity here, you can bound it by -3/4 beta, and this is your spectral gap. So this is the interior region. Sure, we have linear terms, and these linear terms, non-local linear terms, so we can estimate them by the constant that appears in our choice of the weight. Okay, so it's independent of anything. And by choosing this constant arbitrarily large, you can absorb this in the left-hand side. Okay, I promised to finish in 2 regions, so I'll have to skip that. The second region, we apply a maximum principle, and we use a nice property of this primitive equation, saying that after x hat, the flow is moving upward. Okay, so it's not coming back. So all the information is sent from x hat all the way till 1/nu, which is basically very large, which is infinity. Okay, the smooth case. So we were able to show also that we have a blow up. And now what we see, remember the smooth case, this was the case where the pressure cannot be neglected. Okay. And if you don't neglect the pressure, so the interesting observation is that the speed of the blow up is somehow relaxed. Okay, so the speed is somehow slower than the speed when you neglect the pressure. So the heuristic that the pressure is not an enemy for incompressible fluids, we see it in this theorem. And I think I'll stop here. Thank you very much for your attention.